Pacemakers as well as implantable cardioverter defibrillators are two implantable medical devices that both improve lives and save lives every single day. I'm sure that many of our grandparents, as well as maybe someday some of us, will be positively affected by these two medical devices. But I'm sure that when a patient is told by their doctor that they must have one of these devices implanted, I'm sure that it's met with emotions of fear as well as emotions of just not knowing their medical status and worrying about their rates of survival. But these fears about their medical status should not be met with fears about malicious hackers hacking into their implantable medical device and causing them either severe harm or in some cases death. Which is why a lot of scientists are actually researching ways in which these implantable medical devices can be secured. So during the next 20 to 30 minutes, we are going to be discussing my four main points. Number one being, I'm going to explain to you the cardiac conducting system in relation to implantable medical devices. Number two being the security gaps within pacemakers as well as implantable cardioverter defibrillators, which from now on I will just refer to as ICDs. Number three being some proposed solutions for these security gaps. And number four being future research. So now we're going to get into my first main point, the cardiac conducting system in relation to implantable medical devices. So you may be wondering, well, what problems with the heart would cause one to need a cardiac implantable medical device? Well, it's actually a problem in the conducting system. Now, the conducting system is what allows the heart to pump rhythmically. And the problem is actually even more specific than the conducting system. It's a problem with both the AV node, the atrioventricular node, as well as the atrioventricular bundles. Now, the electric impulse in the heart actually starts in the right atrium, and then it must travel down into the ventricles. Now, the atrium make up the top half of the heart, and the ventricles make up the bottom half of the heart. And the AV node as well as the AV bundles are the only way that the electrical impulse can travel from our atria to our ventricles due to a fibrous skeleton that separates the atria and the ventricles, and it is non-conducting. So therefore, if either of these two are damaged, it is known as a heart block, which either prevents the electrical impulse from traveling to the ventricles, or in some cases, makes that electrical impulse travel very slowly to the ventricles. And this causes the ventricles to beat at a rate that is much slower than the atria, which is too slow to maintain adequate circulation. So in this case, your doctor will probably suggest that you get a pacemaker inserted so that you can maintain adequate circulation. So now we're going to get into the mechanism behind a pacemaker. Now the pacemaker is made up of three main parts. We have the battery, the computerized generator, as well as the electrodes. Now the electrodes are able to sense the heart rate, and then it brings that data to the computerized generator. Now if an abnormal heart rate is sensed, the computer will then generate an electrical impulse, which will then hopefully fix the heart rate and bring it back to normal. Also, the computerized generator is able to record both the abnormal heart rates and also the therapies administered by the pacemaker in order to help these abnormal heart rates. And your doctor can then go back and look at this recorded data and use an external programmer in order to better tailor the therapies administered by the pacemaker to your needs. Now we can also talk about a few different kinds of pacemakers. We have a single chamber pacemaker in which the electrode is placed in the right ventricle. And just as I was saying before, a problem with the heart block is that the electrical impulse is not able to pass into the ventricles. So therefore, with a single chamber pacemaker, an electrical impulse is given to the ventricle to help this passing of the electrical impulse. We also have the double chamber pacemakers, in which one electrode is actually placed into the right atrium, therefore helping to generate the electrical impulse, and the other electrode is placed in the right ventricle, helping that electrical impulse to travel. So now we're going to talk about the implantable cardioverter defibrillators. Now they actually have a very similar mechanism to the pacemakers. They are made up of the same three main parts: the battery, the computerized generator, and the electrodes. And they also work in a very similar fashion, being that the electrodes actually, they sense your heart rate. If it's abnormal, the computer then generates, in this case, an electric shock in order to help your heart rate to maintain a normal heartbeat. So now you may be wondering, well, Gabby, what's the difference between a pacemaker and an ICD? Well, a pacemaker is meant to pace your heart, and that if your heart is going too slow, it sends those electrical impulses that would be naturally generated by your SA node, your body's natural pacemaker, whereas the ICD actually acts as a defibrillator. Now, if anyone has ever watched an ER show, or simply any show where one of the characters had to be rushed to the ER due to heart pain, of course we've all seen the doctors have the defibrillators and say clear and shock somebody to life. Well, having an ICD is sort of like having those doctors at the ready at all times. Another thing to note about an ICD is that not only does it have the capabilities to defibrillate your heart, but it could also pace your heart. So an ICD acts as both a defibrillator and a pacemaker, whereas a pacemaker can only pace your heart. Now this is very important due to the fact that in the research that we're going to look at in a few seconds, we're going to see how they're actually doing the test with an ICD, but the security methods that they found can both be used to secure ICDs and pacemakers due to the fact that their mechanisms are very similar. So now we're actually going to get into that research, and we're going to talk about how both pacemakers and ICDs are very vulnerable to software radio attacks and to the fact that they don't have any power defenses. So now here we go. The objective of the research is to evaluate security of communication between the ICD, which is the implantable medical device, and the ICD programmer, which is the device that the doctor will use in order to better tailor the therapies of your ICD to your needs. So, in order to evaluate the vulnerabilities of the communication between the ICD and the ICD programmer, the researchers actually considered three adversaries. The first adversary being someone who has an ICD commercial programmer. Now, the ICD commercial programmer is a programmer that should only be accessible to physicians, but in some cases, those in the medical community who may have access to these commercial programmers can actually pick them up, and they can tailor anyone's ICD to whichever therapies they would like. The researchers found that these ICD programming devices do not have any boundaries whatsoever in order to stop someone who does not have the medical credentials from using the device. Then we're also going to talk about a passive adversary who does not have access to a commercial programmer, but what they do is make an unauthorized programmer using devices such as an oscilloscope, a software radio, an amplifier, and an antenna, which we will see in more detail later in the research. And what they use this to do in the passive case is to simply eavesdrop on communications between the ICD programmer and the ICD, in which they could learn a lot of information both about the patient and the physician. And then we can move on to the active adversary, who uses the same unauthorized program, but in this case, rather than simply eavesdropping on the communication between the ICD programmer and the ICD, they actually have the intention of altering the therapies within the ICD that it would be administering to the patient when they have an abnormal heart rate, which could either cause the patient severe injury or in some cases death. So first off, we're going to start at looking at how the scientists were able to evaluate the passive adversary situation. And in this part of the experiment, the objective was really just to reverse engineer the transmissions of both the ICD and the ICD programmer. So how is this experiment done? Well, they used an oscilloscope, a USP radio, and they also used an antenna. And what they did was attach the antenna to the oscilloscope, and they positioned the antenna between the ICD and the ICD programmer while they were both wirelessly communicating. Now, two main definitions that we're going to be looking at are encoding and modulation. And these two are very important due to the fact that they are the key processes used in data transmission over radio frequency. And the ICD and the ICD programmer are transmitting data over radio frequency. So encoding is when data is converted into a digital format for efficient transmission. And modulation is when converting information to an electronic or optical carrier so that it can be transmitted over a comparatively long distance. Now, in simpler terms, modulation is just making it easier to transfer data over a certain medium. Now, there are actually two types of modulation. We both have continuous wave modulation as well as pulse code modulation. But during this talk, we are going to be focused on continuous wave modulation due to the fact that both the ICD and the ICD programmer transmit their information using continuous wave modulation. Now, continuous wave modulation is when radio waves carry information by altering the carrier wave's amplitude, phase, or frequency, just in order to better transfer the information. So now we are going to get into the result of this experiment. But once again, the researchers were looking for both the encoding scheme and the modulation scheme that both the ICD programmer and the ICD use while they're transmitting data over radio frequency. So they found that when the programmer transmits information, the modulation scheme that it uses is the binary frequency shift keying, which is once again a type of continuous wave modulation in which the frequency is actually altered in order for the information to be transferred. Now this is a binary mode, so the two possible states are both 200 kilohertz and 150 kilohertz. And then if we look at the modulation scheme for the actual ICD, we find that it uses differential binary phase shift keying, which is also an example of continuous wave modulation, but it actually alters the phase in order to transfer the information. So this is once again a binary system. So the two states are either a 0 degrees phase shift, so it's in phase, or a 90 degrees phase shift. So now we can actually look at a sample of the data that they use to look at the encoding scheme that these two programs use. Now I know this just looks like a collection of ones and zeros, but what they were actually able to learn from this is that both the ICD and the ICD programmer actually use the same encoding scheme. The encoding scheme that they use is the ACII, which stands for the American Standard Code of Information Interchange. And also another important thing they found is that both of them use NRZI, which is non-return to zero inverted, which is simply just a serial encoding mechanism. So the one stand for a positive voltage and the zero stand for a negative voltage. Now we're actually going to be able to see a little bit more of the significance of this data in the next portion of the experiment. So now we can move on to, we're still in the passive adversary case, but in the previous part of the experiment, they were simply just trying to find the encoding schemes and the modulation schemes that both devices use in order to better emulate these transmissions when they're actually trying to hack into the device. So now we're going to try to eavesdrop on the communications between the ICD and the ICD programmer, and in order to do that, they had to build their own unauthorized programmer using a USP and a GNU radio. So when they did this, the first thing that they needed to do was study the order in which the ICD programmer received information from the ICD, just so that they could find a pattern in the information, and also so that they can infer meaning in the context by this pattern. Really, they were just looking for when the ICD would be transferring the packet of information that they wanted to hear to the ICD programmer. So they wanted to know when was the right time to listen in on the information. So during this process, they were actually able to find that the packet of information that they wanted to listen in on actually had a beginning byte sequence and an ending byte sequence that signified that the packet of information that they were interested in was in the middle. So each packet of information that they were interested in began with that sequence and ended with that sequence. In the GNU radio, which is simply just a software radio toolkit, essentially, was able to packetize this information for them and block out all the rest of the noise that they weren't interested in. So through this, they were actually able to find that when the ICD programmer and the ICD are wirelessly communicating with each other, the information is not protected and that it can be easily hacked using the tools that we previously discussed. And through this, through eavesdropping on this wireless communications, they were able to find out the patient's name, date of birth, their medical ID number, their history. They were also able to find out the serial and model number of the ICD, and they were able to figure out the physician's name and his phone number. So now we can move on to when they were researching the active adversary case, in which a malicious hacker was not only trying to eavesdrop and gain information about the patient and the physician, but they actually had the intention of changing the therapies administered by the ICD in order to harm the patient. Now, these attacks could actually be described as replay attacks, in which they're going to record a waveform from the actual commercial programmer, record that using their unauthorized programmer, and then replay it back to the ICD, hoping that they can get the ICD to respond the same way it would to a commercial programmer. So now we can actually look at some of the results they found. All the results that they found were pretty positive. They were actually able to record the sequences from the commercial programmer, replay them back to the ICD, and they were able to gain the same results. So some of the things that they did were actually not the most groundbreaking, but they were able to trigger the ICD to identify itself, meaning that they were able to find its model and serial number. They were also able to get it to disclose patient data, and they were able to change the patient's name that the ICD was registered under. They were also able to reset the ICD's clock, which may not seem like too big of a deal, but the clock is used to timestamp both when the ICD administers therapies and when the patient experiences an abnormal heart rate. So it's actually very important for the physician when he goes back to use his commercial programmer in order to reprogram the ICD to better suit the patient. He needs to look at the timestamps of all the events that occurred. And now we're going to get into a bit of the more scarier thing that they were able to do with their unauthorized programmer. They were both able to change the therapies and induce fibrillation. So first we can talk about the therapies. So with a commercial programmer, a physician has the power to either change the therapies and also to shut the therapies off altogether. So what our scientists did was they found the radio frequency command needed to shut the therapies off completely, and they were actually able to successfully shut the therapies off in the ICD using their unauthorized programmer, meaning that when the patient experienced an abnormal heart rate, the ICD would not react at all, and the patient would then be in some pretty severe trouble. And then they were also able to induce fibrillation. Now, when the physicians are implanting the ICD, they actually do a test on it called the electrophysiological study. In this test, it's really just a test that the ICD works properly. So using the external programmer, they use the ICD to put the patient in a state of ventricular fibrillation. And then the ICD is supposed to react with the proper therapy in order to return the patient to a normal heartbeat. But what the hackers did was they turned off the therapies, but still triggered the patient's heart to go into ventricular fibrillation. Therefore, the ICD then wouldn't react with the proper therapy to bring the patient back into a normal heart rate, hence putting the patient into fibrillation without any chance of survival. So I know, guys, this is pretty scary, but now we're going to go into some proposed solutions for these security gaps, so hopefully these things won't happen. So they wanted to find some zero power implantable medical device security and privacy devices. But when looking at this, you need to put a lot of factors into play. So number one, the security apparatus, it both needs to secure the device from hackers, but it also needs to make the device readily available during an emergency situation. And some other three goals that these particular scientists wanted for the device, they wanted the device to both prevent and deter hackers with an unauthorized programmer and also with a commercial programmer. They also needed a security device that did not draw any power from the primary battery source. Now, this is very important because both pacemakers and ICDs have batteries, and these batteries have a shelf life. And when the battery runs out, that whole implantable medical device actually needs to be taken out and they need a new one. So when the battery runs out, it actually needs surgery in order to fix it. Therefore, the security measures used cannot draw upon this new battery source. And the last thing is that when there is a security issue with your IMD, the patient should be able to sense it immediately. So our first security measure is a detection security measure. So they are suggesting that the IMD be equipped with a wireless identification and sensing platform in which if it senses that either a commercial programmer or an unauthorized programmer is attempting to alter therapies, a piezo element will then be triggered and the patient will then hear a loud chirping sound. Now, this is a plausible security measure because it does not draw upon the IMD's main battery source, but one thing to note is that both it's going to chirp if it's a commercial programmer or an unauthorized programmer. All right, and then our next security device that we're going to look at is one that has prevention. Now, this is kind of a cause and response kind of prevention for the security. So let's say a programmer has the intent of reprogramming the ICD. The ICD is then, so this case will have a subscript M attached to it. So the scientists are proposing that each commercial programmer be equipped with a programmer master key. So when a commercial programmer requests to alter the therapies in an ICD, then the ICD will respond with its identity. This is just its identity marker. And then the commercial programmer is supposed to respond with its programmer master key, which will allow it to calculate this number, which will then allow it to calculate this number, and then once the ICD gets this number from the ICD programmer, it will then allow it to change its therapies. So the point is that if it's not a commercial programmer, it will not have the programmer master key, and then the therapies within the ICD will not be able to be altered. Also, another security measure is known as a communication cloaker. So now with the communication cloaker, it's a pretty simple idea that it's a bracelet, and when the patient is wearing the bracelet, their ICD will not be able to be altered either by an unauthorized programmer or with an authorized programmer. If it's their doctor's programmer, it will have a certain key that the cloaker is aware of, so then that will actually be able to alter the ICD. And in an emergency situation, the communication cloaker can simply be removed from their wrist. And now we're going to look at the future research in this field. So as I discussed before, one of the main obstacles when looking at security measures for these implantable medical devices is we need to make sure that our security measures do not draw on the primary battery of the implantable medical device. But there is actually research being done with hopes of removing the battery from the equation altogether. They're hoping that the pacemaker will be able to draw its energy from the heart itself. Now, actually, the people who are doing this research are the Swiss, and the Swiss have an automated wristwatch that doesn't have a battery, but it can keep ticking, and it does that through the movement of the arm. So they're hoping that through the movement of the heart, the pacemaker could actually gain its energy just as the watch. So today, we discussed the cardiac conducting system in relation to implantable medical devices. We spoke about the security gaps within these devices. We also discussed some proposed solutions for these security gaps, and we ended by talking about future research. So, I thank you very much. Are there any questions?